Hello everyone. So I had got a question about iron carbide diagrams, and I am making this video to try and explain iron carbide diagrams in a new way. So please just increase your volumes because this is being done in an informal setting, and so apologies for any mistakes or any, if you hear any sound, please just ignore it. So iron carbide diagrams in general consists of, first of all, the plot. So we have the carbon percentage and we have the temperature. So what is the need? Why do we actually need to know the iron carbide diagrams? The reason is, iron is a structure where you can mix carbon in it, such as you get a huge number of phases and alloys and structures. So to know what is the basic, how does it actually start, so this is the way to start, where they will tell you at what temperature and what percentage, what is the phase that you'll get. So in general, the liquid phase is at the very top, obviously above the melting point, and then as you come, as it cools down slowly, so this is a very slow cooling process, and that is the advantage, or rather that is the significance of iron carbide diagram, that this is a very slow equilibrium cooling phase, a cooling rate, and at that rate you have this kind of a diagram. So you have these different phases, and most of you are very familiar with the iron carbide diagrams. So let's just say, I'll just go through what phases there are. You have the liquid phase here, so everything is in a liquid state. Then you have the gamma plus liquid. In here you have liquid plus Fe3C, that's iron carbide. And then you have the entire gamma phase here. Then you have the gamma plus Fe3C, and you have the alpha plus Fe3C. So basically you have the alpha phase. So these are the different phases that you get at different temperatures and different compositions. Now, if you see, there are a whole number of videos where people have brilliantly explained what these phases are. This video, I'll try to simplify it and will try to visualize it, so how it actually happens. So let me just reorganize the camera and we'll get to it. Okay, so here you have the iron and carbon in a liquid phase, which means that you have these iron atoms and these red ones are the carbon atoms. Now when it is in a liquid state, they are all mixed with each other, as you see. When you have the gamma phase formed, you have the Fcc structure. So in Fcc, you'll basically have the Fcc means phase center. So for each phase, you will have a particular atom. So let's just make a simple 4 square for each, and then we'll add the other atom. So that's a basic cube for iron. And now because so this is a basic cube for iron. So you have iron atoms in a cube form. Now when you have Fcc, you basically have insertion of such kind of iron atoms in each phase. So you will have this kind of 5-phase structure, and as you can see, obviously, because now you have an addition of such atoms in the phases, the size of this Fcc is increasing. The shape will not remain the same. So it looks something like this. So this is how an Fcc structure of iron only looks. So you have this basic cubic structure here with the 4 atoms at the top and the 4 atoms at the bottom, and in each phase you will have one phase centered on. So this is another phase and you have another one. Then this is another phase, you have another one at the phase. So this is a general phase structure. So an austenite usually basic iron structure of austenite will have this Fcc structure. Now let's take a look at what a Bcc structure looks. Now in Bcc, you have a basic base, then you have a body centered, which means you have an iron atom in the center of the body, and then you have the other iron atoms at the top. So you again have the 8 iron atoms at the corners, and you have a central body structure. Now, just by looking at these two structures, you can see the huge difference in their structures. And so this is one of the reasons for the different uh, properties that the austenite and ferrite or BCC would have, because ferrites usually have the BCC structure. So this is what you will see in the gamma phase for the iron, and this is what you'll see in the alpha phase. Now, in this case, you have these spaces in between. So these spaces are the voids, and the carbon atoms will go and fit into these spaces over here. So the gamma phase, when it is formed from the liquid, will basically have carbon atoms fitting into the voids that are present. As it cools down further, you have the BCC structure formed, and in this case you have voids but in different positions and sizes. So there the amount of carbon that goes and fits into these voids is entirely different, which is why the properties of ferrite and austenite are entirely different, because amount and the spaces will be different. Now Fe3C is also something that is formed along with the austenite. So in Fe3C, you have basically an orthorhombic structure. Orthorhombic structure means you have a carbon atom over here, and you have a triangle formed of the iron atoms, then you have a carbon atom, and then you have another triangle formed on the top. So your Fe3C looks like this. So again, when you have a combination of austenite and Fe3C, you have basically a combination of these two. As the iron carbide, you go to lower temperatures on the diagram, you have a combination of these two. So as your composition changes or the temperature changes, the structure that's formed will be different. So this is what makes the makes the composition different. Now let me just go a bit ahead. So these two are now BCC structures. We'll see what happens now. Now you have these two BCC structures, and when it is solidifying, it will join. Basically, it will not necessarily be too different. These atoms will be shared by this, so it will not actually be two different cubes. It will be a joining of these two cubes. So this is how a BCC will look. It's not actually two different cubes. This one will be shared by the other cube, and then you will have the sharing of this with the adjoining structure as well. So you will have these kind of blocks going ahead. It's kind of a pavement, and the carbon atoms will go and stick into the voids that are present over here. So when you have a number of Fe3C going around, you have a combination of these two. So you will have layers of Fe3C going on top or on sides, and you will have alpha structure or ferrite over here. So when you have a slip system, or when something slips, what happens is the slip does not necessarily mean that it will be. So I am removing the carbon atoms just as to make it make it clearer. So when you have a slip system, what happens is they move with respect to each other. So they will move like this, or they will move like this. So they do not actually break open. What happens is there is just a shift in the position of the structure. So this is the slip systems, or this is the way in which the deformations will occur. And the movement of this, if the bonding is different in other atoms, so the aluminum atoms will have different bonding, they will have different structure, atom size, and that will affect how the slip systems will occur. If it is too brittle, so if you see over here, the slip system will mean that the edge, the faced atoms also have to move. So because the face atoms have to move, the slipping in the austenite is entirely different than the body structure. So how is it different? When you are shifting this,
in the center of FCC, you do not have any atom. You only have it in the edges. So when you're shifting this, the faces will move and the atoms over here will move. Here, however, when you're shifting it like this, the central atom will cause some interference in the movement. That's why the mechanical properties or the tensile properties of this will be different from this, because if you just observe from, even in this case, the movement is affected by the body centered atom. So this is a basic example of how it works. Now I've tried to explain it in a simple way. If you have any more questions, you can just get back to me. I'll try to make more of these and we can expand on this topic further. So thank you so much.